Welcome to the lectures on modern digital communication techniques. So, we have seen a particular realization of the detector, where we have started off with the posterior probabilities, that means received a vector R, how would you find which particular signal to be sent, which particular signal was sent, and we needed to calculate the posterior probabilities. We expanded it by the Bayes rule, and then we saw the denominator term has probability of the received signal R, which is independent of SM, and in the numerator we had probability of R given SM times probability of SM, which is the prior probabilities, and then we saw that if the P of SM are all equiprobable, that means all signals are equiprobable, we have the MAP receiver boiling down to the maximum likelihood receiver, and we moved on to see how does the maximum likelihood receiver would look like when we expand the likelihood function. We had taken the log of the likelihood function, we expanded it, and we saw that there is a distance metric that is inherent in it, and maximization of the log likelihood function is same as minimization of the distance metric of the received signal with respect to a particular SM. And there we saw that the distance metric is computed by considering the vectors. So, you could think of the vector R as R1, R2, Rn produced by the output of the matched filter or the correlator, and Sm as Sm1, Sm2 up to Smn, which are the components of the signal, which is already pre-known. So, if you have to calculate the distance between these two, take away take the difference, square it, take the difference, square it up to all the terms and add them together, you get the distance of this vector from this vector, and then you keep changing m equals to 1, 2 up to capital M, and then you choose that m which makes this distance minimum. That is one possible way, and then we looked further and we saw that you do not need to calculate the length of the vector, because when you are calculating the distance, you have the norm square of the vector R, norm squared of the vector Sn, mth signal, and then there is a correlation component. So, since norm squared of R is common for all Sm, so we took that out and we saw that there is a correlation component as well as there is a correlation component and there is an energy component of the signal, which could also be looked at as the bias term. So, when you look at in the integral form, we had the correlation of the received signal R with the different possible waveforms. Take away the bias term of each possible waveform and select the one which maximizes, right. So, these are the two ways of looking at it. So, that means we have the minimum distance or maximum correlation. So, in terms of minimum distance, we briefly stated that suppose you have these constellations that are to be sent. Now, this can be thought of as having a component on the I and component on the Q. So, as if on the I channel this was sent, on the Q channel this was sent, and because of noise this got shifted somewhere there, and because of noise this got shifted somewhere here. So, that means the received signal would be at some location which is here. The minimum distance metric tells that you have to compare the distance with all possible vectors. So, these are the different vectors, right, and you have to see the distance of the difference, which is the nearest distance to it. The shortest distance we identify as the outcome. We also saw this could be calculated as the projection of this vector, we should rather draw with this color, the projection of this vector on all possible vectors and take away the bias term of the signals. Now, from this picture it should be clear why we talk about taking away the bias term, because the energy of this signal is different from energy of this signal. So, you have to take away the bias term and take that output which is the maximum of correlation, that means projection of this on a vector, and taken away the bias term is one of the possible realizations. So, we have seen two possible realizations, but the end result is given a particular received signal, we have to identify which particular signal was possibly sent, which is the possible waveform or which is the possible constellation point which could have resulted in the received signal or the received vector. So, we move on further with this. And we will consider a binary PAM signal for simplicity. Let us move to a binary PAM signal. In the binary PAM signal, you have two signals S1 and S2. This is well understood, we have been discussing this. We have the picture here S1 and S2, and where EB is the energy per bit. So, we also have the prior probabilities P of S1 being P, and since there are only two symbols, the probability of the other symbol being sent is definitely 1 minus P. Now, we have to construct a map detector for this particular example. So, to construct the map detector, we must remember that we are dealing with a binary PAM which is one dimension, right. So, that means there is the matched filter output projects the signal on one of the dimensions and it gets a single component. So, the received vector, received signal R can be written as plus minus root over EB, because your signals that we have here are root over EB and minus root over EB, which is also described in this particular statement here. So, when we have the received signal as either plus or minus root EB, that means S1 or S2, and there is the noise component. So, this is the outcome of the matched filter at the end of the sampling time t. So, this is the received signal vector. So, this part we have already seen, it is 0 mean with the variance of n naught by 2 in our earlier discussions. So, when you have to construct the map detector, remember we have to construct P of R given Si multiplied by P of Si. This is what we had said, and find that I which maximizes this, right. So, just reminding what we had discussed earlier. So, we need to calculate a P of R given S1, and P of R given S1 is simply R minus root EB, because this is the mean of the signal and this is the distribution of white noise. P of R given S2 would be plus EB. In one case you have minus EB, because in one case the mean is EB, the other case the mean is minus EB. So, R minus EB is plus EB, that is what we have. So, now the map metric would be Pm of R with S1, right. Probability metric of R and S1 would be P, that is the probability of sending S1 multiplied by probability of R given S1, right. So, that is P because of this P multiplied by whatever we have over here. So, this comes there, and this is P of S1, right. And then the probability metric that or posteriori metric that we have to calculate is P of R with S2 is 1 minus P, because this is P of S2 a priori probability. If P is the probability of S1, 1 minus P is the probability of S2, we have already said that, and this we again have from P of R given S2. So, now our job is to select S1 or S2 depending upon which particular metric gives the higher value. So, we could say that we have a decision rule in a way that we take the ratio of the metric of R on S1 and R and S2, and it is also sometimes called as the likelihood ratio test. So, these are the likelihood functions of R with S1 and R with S2, and we are taking the ratio of them. So, if this ratio is greater than 1, my decision would be S1. So, that is why we have, if it is greater than 1, it is S1, and if the numerator is less than the denominator, that means if the denominator is greater, then you have it less than 1, right, or in other words, if P of m r S1 is less than P of m r S2, then definitely S2 was the transmitted signal, and as per the decision rule. The decision rule tells you calculate this probability matrix, whichever probability matrix gives a higher value, you choose that particular signal. So, now we have computed this probability matrix here, we have already computed this probability matrix. So, we are saying you divide them, take the ratio. If you take the ratio, you are going to have P upon 1 minus P, this and this would cancel out, this particular term would cancel out with this term, and in the numerator you are going to have this term minus this term, right. So, that is what we have, the and since it is in the denominator, it goes up. So, there is a plus sign, of course. So, you have P 1 minus P, that is what we just stated, e to the power of this term which has come from the denominator minus this term, right, and the right hand side remains the same. That means, if this is greater than 1, you would choose this to be S1, if it is less than 1, you choose the signal to be transmitted as S2, and that is the output of your decision device. So, what we have in the next step is 1 minus P upon P. So, 1 minus P upon P, and since this is E, so when it goes to the right hand side, you have an ln. So, you have this term ln of 1 minus P upon P, and this denominator 2 sigma n squared is getting multiplied. So, we have this term. So, you are left with only this distance on the left hand side, and the right hand side you have this. So, again reminding that if this is greater than this, our decision is S1, if this is less than this, our decision is S2. If you do a few steps algebraic operations, you are going to get r squared terms which are going to cancel out, then you are going to get 2 r root E b, and there will be 2 root r E b. So, you are going to get r multiplied by E b, and then you have E b squared, you have E b, and they will also cancel out. So, you are going to left with 2 times r E b multiplied by 2, and there is one factor of 2. So, one of the 2 cancels out. So, you are left with 2 r root E b, right, and then you could bring the 2 E b 2 root E b on the right hand side, you will be left with if r. So, what is r? R is the output of the matched filter in case of PAM. If it is greater than the right hand side, which is here, then your decision is S1. If it is less than the right hand side, your decision is S2. So, the right hand side, again you could say that sigma squared n is n naught by 2. We had chosen that sigma squared n is n naught by 2. So, what you have is n naught by 4 and the expression as it is. So, you could say whatever is the outcome of the matched filter, if it is greater than this expression, I would choose it as S1 and I would choose this as S2. So, what does it mean? Let us take a look at this. So, as if right. So, if we have this with us, now things will be a bit better. So, as if this is my signal space and we said that one of the signal is root E b, the other signal is minus root E b, and now this has a probability of, so this is S1, this is S2, probability of S1 being sent as P and probability of S2 being sent is definitely 1 minus P, and then the matched filter produces some R. So, if you have let us say S1 which has been sent, suppose some particular signal has been sent, noise will corrupt it and it will be somewhere. If S2 would have been sent, noise would have got added and it would have been somewhere. So, now suppose which one is sent we do not know, but we have received an R which is here. So, let this be R. So, what it tells is you compare R with this particular value, right, and if R is greater than this value, then you choose it to be S1, and if R is less than this value, you choose it to be S2. So, now let us take a look at how this is important. So, if P is equal to half, so if P is equal to half, so that means you are going to get 1 minus half upon half and ln of that, so which will be 0. So, 0 on the right hand side, that means our decision R will be compared with this point of 0. So, if R is greater than 0, then you would choose it as S1, and if R is less than 0, you would choose it as S2. So, this also conforms to the nearest distance or the minimum distance criteria. So, we could say that this is the region for this particular case. Now, if instead of this situation you have, suppose, so I would rather make this with this color to indicate the same. Now, if you have P to be greater than half, right, if P is greater than half, that means S1 is getting transmitted more often than S2. So, if S1 is plus 1, S2 is 0, that means we have a sequence where there are more ones than zeros, right. So, if P is greater than half, so if P is greater than half, we would look at this expression, the numerator is less than the denominator, right. P is more than half, numerator is less than half, 1 minus something more than half, denominator is half. So, that means log of some number which is less than 1, therefore, this is negative, right. Therefore, the log of a number which lies between 0 and 1 is negative. So, that means in that case you have, so this right hand side, this thing we could mark it as tau h, that is a threshold. So, in that case we could say this is, let us say, tau h. So, if R is greater than this, you would select it as S1, if R is less than this, you would select it as S2. So, now we can see that if in this case we know the prior probabilities, then the way we implement our receiver would be, you simply get the output of the match filter, compare it with a threshold which requires the knowledge of N naught, EB and P, right. P is the probability of transmitting a particular constellation. It requires N naught, EB, because accordingly things get scaled. So, if P is some value greater than half, let us say it is 3 by 4, say it is 3 by 4. So, this has a particular value and this is going to scale that. So, depending upon a certain EB by N naught, your TH is going to vary, right. So, you need the ratio of EB with N naught and you need the value of P which is going to produce the value of TH. You are going to compare R with that TH and then you are going to make a choice that which particular signal was sent, and we would call this region R1, let us say, and we will call this region, let us say, region R2. So, if R falls in the region R1, we would say S1 is sent. If it falls on the region R2, we would say S2 has been sent. Now, suppose you have certain prior probabilities, but instead of implementing the map receiver, you start to implement a ML receiver. So, if you implement the ML receiver, that means you are going to choose P as half equal probable. That means this term is going to be 0, TH will be 0. So, now whatever is the transmission probabilities, you will take the received signal and compare it with the midpoint, mid distance between these two constellation points, right. So, you are going to get a certain probability of error which will be different from the map receiver. Only when the probability of transmitted signal is equal to half, then only the ML receiver and the map receiver is going to produce the same outcome or the same performance in terms of error probabilities. So, with this we would like to move on to look at another interesting thing. So, and look at how the receiver structure would be like. So, now we would like to take a look at the situation when the transmitted signal has memory. So, when the transmitted signal has memory, the signals transmitted in the consecutive intervals are interdependent, right. Definitely the output now is dependent on the output before plus the incoming information sequence. In that case, the optimum detector, which we have just discussed, should base its decision on observation of the sequence of received signals over successive intervals. So, what it means is that suppose I have a signal which is present here, followed by a signal there, and then maybe the next signal is this one. In the previous case, we said that this signal is independent of this signal, which is independent of this signal, and so on and so forth. But now we say that this signal is dependent on this signal. So, there is some kind of an XOR operation or some other thing. For example, we use NRZI and things like that, where you use the prior output which influences this output. So, the original information sequence is actually spread across more than 2 symbols. In that case, all it says that when we design the receiver, we should not base our decision on only one observation interval. We should base our outcome by looking at several observation intervals in a sequence. So, like we have to do the similar thing that we have done before, but we are going to do for multiple signals, multiple signal intervals. So, this is the example of NRZI, where you have this XOR operation, and let us take binary PAM modulation S1 and S2 as. So, the NRZI signal is the information bearing signal where there is an XOR operation, and the outcome is still a 0 and a 1, which is used to modulate the PAM, right. So, using that, the output of the matched filter in the kth interval. So, please note we are changing the notation slightly. So, now k is not indicating the n components, it is just the kth signal interval, because we are using so many variables, it is very difficult to have unique notations. We are reusing one of the notations. So, R k, the received signal in the nth interval, not the kth component, is equal to plus minus root E b plus n k, which is same as what we had indicated before, and description of n k is the standard description that we have. Now, if S1 was sent, probability of R given S1 is what we had seen earlier, and probability of R given S2 is this, which is here is a minus sign, here is a plus sign, we had seen it just a few moments before. So, now R1 to Rk be a sequence of matched filter outputs observed, right. So, I would like to remind once again. So, R1 to Rk would be the output of the matched filter. At this point is R1, at this point is R2, at this point is R3, and you will have Rk, right. So, these are not the components of the received signal. Earlier we had the received signal in this interval, and this was decomposed into its components R1, R2 up to Rn. So, the notation might be confusing. So, please do not get confused with the components. We are talking about sequence of matched filter output observed, and f, that is the basis functions, are orthogonal for 2 different time intervals. That means, if I and j are not equal, they are orthogonal, right, and that is clear because the basis function is here, the basis function is there. So, the basis functions are like this. So, this is orthogonal in this interval, right, that is what it simply says. And the noise in these two intervals, the noise component here and the noise component here, are again uncorrelated and hence independent, right, that is what we have. So, now if we consider a given sequence S m, so we now have m in the power to indicate it is a sequence. Earlier we had written S m, so please note the notation is not the same. Here you have m possible different waveforms, but here this is a sequence, that means one signal, another signal, another signal, another signal. So, we are sending these signals out. Then the joint PDF of these received signals in these k observed interval, since we said them to be independent, noise is independent and these basis functions are orthogonal, similar conclusions as we had for the components. The logic is the similar and the conditions are similar. So, the conditional distribution would become the joint distribution would become the product of the individual distributions. So, now similarly as we had before, the expression looks quite similar, except the meaning of these terms are different than what we had used before. So, now we have given the sequence of observations R 1 to R k, the detector determines the sequence S 1, S 2 up to S m k. So, look at this, we have these different signals in different intervals that have been sent, right, and this combination is the sequence S m, right. So, if I have let us say two symbols and I have two possible symbols, let us say plus d and minus d, and I observe over 1, 2, 3, 4, 5, 6 possible intervals. So, here there will be two possible sequence, two possible options. So, you have 2 to the power of 6 possible waveforms or 2 to the power of 6 possible sequences. One sequence is all plus d, another sequence is probably a plus d, a minus d, a plus d, a minus d, and so on and so forth. The other sequence could be, then another sequence could be. So, these are all the different possible sequences and each of the sequence is indicated by this. So, note in this case our capital M is 2, however, we have 2 to the power of, so this is m to the power of k possible such combinations. Similar thing, similar logic we had used in source coding. So, I mean should not be confusing at this stage. So, now if you look at it, what it is trying to do, it is trying to find, we have the similar expression as we had for MAP receiver or ML receiver. Now, what we have over here is the distance of the received sequence from a particular sequence. So, we are not talking about a particular symbol, but we have a particular sequence. So, this is the distance, right. So, detector determines which sequence, which one of these sequence. So, one sequence could be all plus ones, one sequence could be like this, another sequence could be. So, the detector, another sequence could be, the detector is trying to find out which of these sequences could have been sent, and hence this kind of a receiver is known as the maximum likelihood sequence detector. So, it is not just the maximum likelihood detector, it is the maximum likelihood sequence detector. If you had to use the prior probabilities, then you had to multiply over here the probability of each possible sequence. Now, generally again we are assuming here, if all sequences are equiprobable, then we need to just look at the particular possible sequence that could have generated this particular outcome. So, this particular part that we have discussed in the last part of this particular lecture is just for your information sake, because this kind of maximum likelihood sequence detectors are used in complex receivers where you have some kind of a Strelly structure or memory that gets involved during the transmission, or maybe when it passes through a channel and you would combine and you would like to decode the signal simultaneously with respect to channel equalization. So, this particular part is for your advanced knowledge state but you may not use it in a very simplistic receiver, and there could be other ways of extracting the benefits as shown by these kind of receivers. Thank you.